Driving your car with the fuel low warning light constantly glowing might seem like a harmless habit, but it is quietly destroying your electric fuel pump. Here is the exact physics of what happens inside your gas tank when you drive on empty, and why it will eventually cost you over $1,000 in mechanical repairs. To understand why running low on gas destroys engine components, you first have to understand the mechanical design of a modern automotive electric fuel pump assembly. In older carbureted vehicles, mechanical fuel pumps were bolted to the outside of the engine block, drawing gasoline using a simple rubber diaphragm driven by the camshaft. However, modern fuel-injected vehicles require vastly higher fuel pressures, ranging from 40 to over 80 psi for traditional port injection, and reaching thousands of psi for high-pressure direct injection systems. To generate this constant, high-pressure flow, modern automakers install a high-speed electric turbine pump, submerged directly inside the plastic or steel fuel tank itself. This submerged electric fuel pump consists of a small, high RPM electric motor connected to a plastic or metallic impeller. It sits inside a plastic housing known as the fuel pump module or bucket, which also houses the fuel level sending unit float, a coarse inlet strainer mesh, and the primary fuel pressure regulator. When you turn your ignition key or push the start button, the engine control module energizes the fuel pump relay. The tiny electric motor inside the pump spins at speeds upwards of 10,000 revolutions per minute, drawing raw liquid gasoline from the bottom of the tank, pushing it through the fuel filter, and sending it down the high-pressure fuel lines toward the engine's fuel rail. Now we have the two critical roles of gasoline, cooling and lubrication. The most critical engineering fact that 80% of drivers do not realize is that gasoline is not just the fuel that burns inside your engine. Gasoline is also the coolant and lubricant for the electric fuel pump motor itself. Unlike standard electric motors found in household appliances that use external air cooling fins or cooling fans, an in-tank fuel pump relies entirely on liquid submersion. As liquid fuel is drawn up through the bottom strainer and pumped directly through the internal electric motor assembly, it absorbs the intense friction heat generated by the spinning armature, copper windings, and brushes. Furthermore, liquid gasoline acts as a hydraulic lubricant for the microtolerances inside the pump's spinning impeller and internal steel bearings. When your gas tank is full or half full, the fuel pump module is completely submerged in gallons of cold liquid fuel. This surrounding liquid bath dissipates ambient electrical heat, keeping the pump motor operating at a stable, cool temperature. However, when you allow your fuel tank level to drop down to the absolute bottom, right around or below the low fuel indicator warning light, two destructive physical phenomena immediately begin to occur. First, the pump is exposed to open air. With no surrounding liquid fuel to absorb dissipated heat, the electric motor's internal copper windings rapidly overheat. The temperature of the pump casing spikes, causing the protective insulating varnish on the internal motor wiring to break down, melt, and short out over time. Second, the pump begins sucking air bubbles. As you accelerate, brake hard, or take sharp turns with only a gallon or two of gas sloshing around a wide, flat fuel tank, the fuel pickup strainer momentarily uncovers. The high RPM pump sucks air pockets instead of continuous liquid fuel. Without liquid fuel passing through the internal bearings for those brief seconds, the pump loses its lubrication film, resulting in instant metal-on-metal microfriction, bearing wear, and scoring inside the pump housing. We continue with the dirt, sediment, and debris trap. Beyond thermal degradation and starvation, driving on an empty tank exposes your fuel system to a severe contamination threat. Bottom tank sediment and rust buildup. No matter how clean the fuel is at your local gas station, every fuel tank accumulates microscopic debris over years of operation. Dirt, sand, rust particles from aging station storage tanks, and airborne dust particles introduced during fill-ups gradually settle at the absolute bottom of your vehicle's gas tank. Furthermore, moisture from ambient humidity condenses inside the empty airspace of a low fuel tank during temperature fluctuations, especially overnight. Because water is denser than gasoline, this condensed water settles directly at the bottom of the tank underneath the fuel layer. When your tank is well filled, these heavy contaminants and water droplets stay dispersed across a large volume of liquid, resting below the effective suction height of the fuel pump module. However, when you run the tank down to the absolute last drops of gas, the fuel pump strainer is forced to pull liquid from the absolute lowest floor of the tank. The pump continuously sweeps up this concentrated slurry of fine dirt, rust scale, abrasive sediment, and condensed water droplets. While the coarse mesh strainer on the bottom of the fuel pump module stops large pebbles and debris, microscopic abrasive particles pass right through the mesh. These abrasive particles hit the spinning impeller at 10,000 RPM, scratching internal clearances and eroding the tight hydraulic seals necessary to maintain high fuel pressure. Downstream damage, injectors and catalytic converters. The destructive consequences of driving on empty do not stop inside the gas tank. A failing, overheating, or contaminated fuel pump creates a severe domino effect that damages expensive components up front in the engine bay. As an overheating fuel pump loses internal pressure due to scored impellers or damaged electric motor windings, it can no longer deliver the required fuel pressure and volume demanded by the engine control module. Instead of spraying fuel at a crisp 40 or 60 psi, the pump pressure drops to 20 or 30 psi. This loss of line pressure causes the fuel injectors to spray a weak, poorly atomized drizzle of fuel rather than a fine, vaporized mist. This weak fuel delivery creates a severe lean air-fuel mixture inside the combustion chambers, meaning there is far too much air and far too little fuel. A lean mixture burns significantly hotter than a proper balanced mixture. High combustion temperatures cause cylinder hot spots, engine pinging, and spark plug electrode erosion. Even worse, when the fuel pump momentarily starves while you are accelerating onto a freeway or climbing a steep hill, the engine experiences violent lean misfires. When a lean misfire occurs, unburned oxygen and raw, unburned gasoline droplets exit the cylinder and travel down the exhaust manifold straight into your red-hot catalytic converter. The raw fuel ignites inside the microscopic honeycomb structure of the converter, causing temperatures inside the catalytic converter to spike past 1800 degrees Fahrenheit. Within minutes, the internal ceramic core melts, fuses shut, and completely destroys a multi-thousand-dollar exhaust component. We finally have the cost breakdown and prevention. Many drivers treat running on empty as a budget-saving strategy, putting $20 of gas in the tank at a time instead of filling it up completely. But from a financial perspective, this habit is an absolute money pit. Replacing a burned-out electric fuel pump is rarely a simple $50 fix. In almost all modern vehicles, replacing the pump requires 1. Labor-intensive tank removal. Mechanics must disconnect exhaust heat shields, drive shafts, and EVAP lines to drop a heavy, awkward fuel tank from underneath the chassis, taking 3 to 5 hours of shop labor. 2. Expensive assembly units. Automakers sell fuel pumps as complete modular assemblies that include the pump, level sender, housing, and pressure regulator, easily costing anywhere from $300 to over $800 in OEM parts alone. 3. Secondary flushing. If the pump disintegrated and shed metallic debris or melted plastic into the lines, the entire fuel system must be flushed and the high-pressure fuel filter replaced. A typical fuel pump replacement easily reaches $800 to $1,500 at a certified repair shop, all because of a habit that saved $0 at the pump. The mechanical verdict is clear. Your fuel gauge needle should never be viewed as a range finder to see how far you can push your luck before walking to a gas station. To protect your fuel pump, preserve your fuel injectors, and avoid sudden breakdown costs, adopt the golden mechanical rule. Treat the quarter tank mark as your absolute empty mark. Refilling your tank whenever it reaches 1/4 remaining ensures your fuel pump stays completely submerged, cool, and fully lubricated, while keeping tank sediment far away from your engine. If you found this mechanical breakdown helpful, hit the like button, subscribe to the channel, and drop a comment below letting us know. Do you fill up at a quarter tank, or do you play gas lamp roulette? Keep your tank full and keep your intake breathing freely.